Hey everybody, my name's Andy Williams, and today I'm going to be talking about springs and such, things like that. So, the purpose of this lab was to analyze the motion of a mass on a spring using Newton's second law and the energy principle. The motion was analyzed using the tracker software, a computer model was made, and then they were compared. When the two were compared, they were similar at first, but they got off a little bit over time, but that's alright. So, here are the physics principles that we're going to look at. Newton's second law and the energy principle were both involved in predicting the motion of the system. Newton's second law helps to predict the new velocity and the position. The energy principle told us that the energy of the system equaled the kinetic energy plus the potential energy of the spring plus the potential energy of gravity, and that's down here. Now let's take a look at the video in Tracker. Now I actually accidentally deleted all of my Tracker 5 seconds before I tried to make this video, but this is basically how it looked. You track the points and it shows it right here on the X plane. So the data was then placed in a CSV file, which we'll look at in the code, and the two graphs were made to show oscillation tendencies. So now here is some of the VIDLE code that was used to make the computer model. The initial conditions are shown in this picture. The initial mass is right here at 0.402 kilograms. The position was taken from Tracker at negative 1.113 for my x and y right there. The ball velocity started out at 0, the time was 0. Now here's where we created the CSV file, and the time step had to be very small, which is why it's 1 divided by 210. Now let's look at a little more of the code that's more involved in this lab. So using these equations on the left, I was able to calculate the spring force, the spring constant, the L naught, which is the relaxed length of the spring. L hat tells us the direction of the spring force, which is important. And then S tells us the magnitude of the stretch or the compression. Now moving down, this is the energy stuff. You have the kinetic energy equation right here. You have the potential energy of gravity and the potential energy of the spring. Now these equations right here were used to calculate. This is all this in code form. Now moving down, we have the force of gravity, the force of the spring, which is just the spring equation. You have F net, the ball's velocity from Newton's second law, the position from Newton's second law essentially. You have L hat again, all of that from before, and then you have all of this down here. Now, this code updates the stretch, compression, and position of the spring right here. They make the visual model change as well. So this code group updates the energies related to the system. Now, let me run the code. Actually, I hope it works because I changed my tracker. Oh, it works. Great. So, right here we have the red ball, which is my actual data. So it's running. The blue ball should follow it from the computer model. Now we see it does a pretty good job, but as it gets closer to the end, it gets off. Now this is because drag kind of catches up with the mass and because of human error in Tracker. But I think it does a pretty good job, and it's cool to see this pattern. Now over here we have the energies graphed. The blue line is the change in kinetic energy. The red line is the change in spring potential energy. The green line is the change in the gravitational potential energy. The yellow line is the change in total energy. Now it's important that yellow is on 0. We'll talk about that later. Now let's answer the questions. The energy principle is satisfied by what we saw in Tracker and in the computer code. Even though the gravitational potential energy, the spring potential energy, and the kinetic energy change and go up and down, the yellow line, which is the total energy, stayed at 0. That's why the energy principle is satisfied. Now, the oscillation periods for X and Y are shown here. This is X and this is the Y. The X oscillation time was about 1.7 seconds, and the Y position was about 1.5 seconds. Now, the reason they're different is because the motion of the spring was an elliptical pattern. It wasn't perfect. So it took longer for the X to oscillate than the Y, which is supposed to be expected. So, thank you very much. That's my lab.